Hello, everybody. My name is Masood Olia. I'm a professor at Wentworth Institute of Technology in the School of Engineering. And I'm here with an example, a problem related to the subject of dynamics. It's a very simple problem where you're given acceleration as a function of velocity. So remember, acceleration could be a function of time, could be a function of position, could be a function of it could be constant. In this case, acceleration is given. So let's start working on this problem. Given, let me just get to my draw. Given acceleration as a function of velocity, and it's equal to -2 times v. So it's a simple, a function of velocity. So in other words, if you plot acceleration versus v, right, it would be basically a straight line with a slope of -2. So when acceleration is 0, velocity is 0. When, for example, velocity is 1, acceleration is -2. So it will be a line like that. Okay. So the question is, if we are given some initial condition that at t equal, for example, 0, s is 0, and let's say velocity is 20 meters per second. So we establish our unit as metric system, right? So now the question is, if these are given acceleration as a function of velocity and we are given the initial conditions, we want to find position as a function of time, s as a function of time, velocity as a function of time, and acceleration as a function of time. Notice that now we want to find everything as a function of time. We already have acceleration as a function of velocity, right? So the question is, how do we do this? So if you look at the definition of acceleration, acceleration is what? dv dt. So with just a minor arrangement that you can do, basically put dt here and a in place of dt. You get dt equal dv over a. Right? See, since acceleration is a function of velocity, you want to make sure that a and dv are on the same side. So in this case, if you go ahead and integrate, you should be able to integrate acceleration as a function of velocity. So I'm going to go ahead and redo this here. Say, instead of a here, I put -2v, right? And I integrate, and I'm not going to put the limits of the integral, since eventually I don't want instantaneous position or instantaneous velocity or instantaneous acceleration. I want them as a function of time. So I'm going to treat this as an indefinite integral, meaning I'm going to get a constant of integration. So the integral of dt becomes t. Well, basically, I can write this as -1/2 dv over v. You know, the integral of dv over v becomes natural log of v. So actually, you pretty much have now plus a constant of integration. I totally forgot about that. Plus a constant of integration that now we can find by saying, okay, at t equals 0, v is 20. So when t is 0, I'm just applying the initial condition to find the constant. So basically, c1 becomes 1/2 of log 20. So if I rewrite this now as t equal -1/2 log v plus c1, which is now is 1/2 log 20. Now I can, make this, a little bit cleaner by, say, for example, I'll take, first of all, I can multiply everything by 2. So I get a 2t equal minus log v plus natural log of 20, right? And since I want to isolate log v on one side, so eventually get v as a function of time, I'm going to do this. I'm going to take log v to the left and bring 2t to this side, so minus 2t plus log 20. And now I'm going to take the inverse log. So this basically, in other words, e, like that. Use e to this power and this power. So I end up getting v And e to the power minus 2t plus log 20, you could leave it like that, but we can make it a little bit cleaner. You know that you could break that into e to the minus 2t and e to the log 20, right? And of course, e to the log 20 becomes just 20. So v eventually becomes 20 e to the minus 2t. Here we go. So here's your velocity as a function of time. So what else we are trying to find? We are trying to find acceleration as a function of time. Actually, this is very simple. You could either take the derivative of, you have two options. Acceleration is dv dt, so you could go ahead and take the derivative, which is very simple, becomes minus 40 e to the minus 2t. Or even easier than that, remember at the beginning we said the acceleration is what? Minus 2v. So if you already have velocity right here, see, it does give you exactly the same thing. So we got two of the things that we wanted to find. Now we go ahead and we say, okay, how do we find S, position as a function of time? Well, we know that velocity is derivative of position, right? Rate of change of position. Therefore, ds is the integral of v. So I go ahead and I put v, which is 20 e to the minus 2t, and I integrate it. Again, I'll just try to use the initial condition. So the integral of ds obviously is s, and the integral of that becomes 20 over minus 2 e to the minus 2t plus a constant of integration. I call it C2. Let me move this up. So s becomes minus 10 e to the 2t plus C2. So now, what was the initial condition? When t is 0, s is 0, right? So s is 0, when t is 0, of course, this term becomes just minus 10. Therefore, C2 becomes positive 10. So here we go. S as a function of time becomes minus 10 e to the minus 2t plus 10. So we ended up finding the position, velocity, and acceleration as a function of time. Remember, the key was our acceleration was a function of velocity, not function of time. So we had to go through this rearrangement of definition of acceleration and then just do integration and manipulate the equation. Okay, thank you for watching and listening. We'll be back with more videos for you soon. Thank you again, and see you soon.